Parissis from University of the Basque country. The title of talk is his talk is Directional Singular Integer in Codimension 1. So with this, I would like to invite him to give a talk here, and I would also like to thank him for accepting the invitation to give a talk here. I also request all the participants to mute their microphone. With this, I would like to invite Ioannis to give his talk. Over to you. Thank you.
Thank you very much. Thank you very much for the invitation. It's a great pleasure and great honor. I will talk about some joint work with my colleagues Ioannis Bakas, currently at the University of Patras, Francesco Di Plinio, who's in Napoli, and Federico II, and Roncal here in Bilbao at BCAM. And this is a work in the general area of directional singular integrals, and I will try to give you background and sufficient somehow motivation and information to maybe try to appreciate the content and the research questions. So let me begin, and feel free to interrupt me, or if there is any problem with the slides, please let me know. So I will talk about two main objects. I first introduce these averages, which you can think as operators acting on functions in Rn, functions of n variables, and these averages just average along a certain segment centered at x and scale r, and v is the direction of the segment. So think of a segment centered at x pointing at a unit vector v, and this is an average at scale r, and then there are two maximal versions of this operator. The first is maximum supremum over all directions in a certain subset of the unit sphere. We will see what are the possibilities for this capital V. And the second is the one where we also take supremum over scales. So the length of the segment is R, okay? And I take supremum over scales. And now note here that I will be interested in LP estimates for these operators, and these LP estimates are scale invariant. So if one is going to study the single scale operator with fixed R, well, we might as well take R equals 1 because the estimate is scale invariant. Okay, so you can think of the single scale operator as an average at scale 1. And now there is a singular integral version. And let me point out something here. So usually we think of maximal operators, geometric maximal operators, as non-singular, or in any case less singular than the corresponding, let's say, singular integral. But here we are in Rn, and this average has a lower dimensional kernel. In fact, it's a one-dimensional kernel. So there is singularity coming from the support of this kernel. So you can think of this as convolution with a measure supported on a segment. And that's already singular because of the lower dimensionality. However, when we look at singular integrals in the directional world, there is also the singularity at the zero frequency. So the prototypical example is the Hilbert transform, where again, I fix a direction, I take a function in n variables, and I look at the Hilbert transform of this function along the line x plus v and t, spanned by v. And v is again some fixed direction, right? And now I can describe this on the frequency side by using the multiplier of the Hilbert transform up to a constant that I won't care about in this talk. And just a different way to write this, it's not point-wise equivalent, but essentially it's a combination of this guy with the identity, is to think of the multiplier, which keeps only the frequencies of f in the half space c dot v greater or equal than 0. Okay, there will be a picture very soon. This is just because it's easier to draw pictures with this multiplier. And now there is nothing really special about the Hilbert transform here. One could think of a general Hellman-de-Michel multiplier and consider the corresponding directional singular integral. And Hellman-de-Michel, I mean here that I have as many derivatives as I need. I don't care about the number of derivatives, and the derivatives of, sorry, this will be m here, of the multiplier decay with the distance to the origin, which is the singularity of the frequency singularity. And okay, for these operators, if I fix V, well, there is nothing to them because they act trivially on the perpendicular variable. So Fubini will tell you they are bounded. But the interesting things happen when I take supremum over direction. So these are the maximal versions in terms of the set of directions. And now these are the frequency images here. If I look at the multiplier for the average, this
can
is.
you go back to previous slide?
Yeah.
So this HMRN is this. What is this HMRN?
So this is I just define a norm here, the Hermander-Michel multiplier norm, where I normalize the constants of the multiplier. So the essential assumption for the multiplier is that if I take alpha derivatives, and this again, this is a typo, this would be M. If I take alpha derivatives, they decay as 1 over C to the order of the derivative. And this X's you should think of as distance from the origin, which is the frequency singularity. And now I just assume that I have M derivatives, and M will be as big as necessary here. Okay. And I just define this constant because I want to normalize the assumption, because the assumption will be uniform for all multipliers for which this is 1, say. Okay. So I want to normalize the assumption of the multiplier. That's all. And this will be somehow relevant later on because I'll look at families of multipliers which have uniform Hermander-Michel bounds. Okay, that's why I introduced this quantity here. Okay, so these are the frequency pictures. The average projects on a band, which is a neighborhood of V perp. And at what scale? It's a scale 1 over R. So the space scale is R, the frequency scale is 1 over R. And here the maximal function is a positive operator. I can smooth it out. And instead of having a rough projection, I can have a smooth bump adapted to this band. Okay, this is pointwise equivalent. And so one can think of the multiplier of the directional average as a smooth projection on this band. And now for the directional Hilbert transform, I fix V, I take V perp, and this is the projection of the half space I was talking about. So you take F, you keep the frequencies on this half space, and you just forget about the frequencies in this Xi dot V negative half space. Okay, this is what these multipliers do for fixed V and fixed scale in the case of the averages. And a usual and useful device when you have supremum, you have maximal operators, many times we want to linearize them. And this is done as follows. So I have a supremum over, say, V in these operators. So for each point X, I can find a V, which is a function of X, that more or less achieves the supremum. Okay. And a priori, this is just a measurable map. So for each X, I find a V that achieves the supremum in directions, and a priori, this is just measurable. And by this kind of way of thinking, I define a measurable vector field of directions. So for each point X, I define the V. Okay. And this is a way to linearize these operators. And a notation that I will be using is if I want to, instead of looking at all scales here, I want to truncate the scales, I will introduce some cutoff S. Okay, so I will only look at scales up to S, both for the average and for the Hilbert transform here. And this will become relevant very soon. Okay, so this I average only up to scale S. And here, this is the sum of the little Pelli pieces, let's say, up to some scale 1 over S, more or less. Okay. Now, the first important obstruction is the counterexamples that these operators have to face, and the most important one is Kakeya type. So let's draw a picture in, say, in 2D. These are delta times 1 tubes. They have cross-section delta and length 1. And these are 1 translates of these tubes, meaning that I take this tube and I translate it in its direction by 1 length. The length is 1, okay? And let me call T tilde these translated tubes and T the original tubes. And now what is my set of directions here? Essentially, if you think about it for a moment, you realize that I take a delta separated set on the unit sphere, and I call this a delta net if it's a maximally delta separated set, okay? And this is because of the delta fatness of the tubes. these tubes don't see directions that are closer than delta. And now there are very well-known and classical constructions, originally going back to Pesikovich and then to refined by Schoenberg and Cordoba, that say that I can arrange these tubes essentially to be in a delta neighborhood of a Kakeya set, so that the translates are disjoint, okay? And since the translates are disjoint and each has a measure delta, you can see that there are 1 over delta of them, so the measure of the union is roughly 1. While if I sort of compress them, right? So this is the Kakeya phenomenon. You have a bunch of tubes lying in space, and now you are asking, how can I put them all together so that I have the minimum volume of the union? And this is achieved by the Kakeya set. The maximum compression you can achieve is 1 over log 1 over delta. This was essentially due to Besikovich with an extra log factor and then refined by Schoenberg. And the fact that this is actually possible and you cannot do worse, let's say, is due to Cordoba. So if you think about it for a moment, if you take the indicator function of this union of the tubes, you will see it's a counterexample for these operators. You will see immediately that plugging in as a function the indicator of this union, you get these lower bounds. As delta goes to 0, this blows up, which tells you that if you want bounded operators, the set of directions cannot be arbitrary. In particular, it cannot be the whole unit sphere or unit circle, and cannot even be an arc, okay? And in fact, there are many cases where you can construct a Kakeya set. For example, if you take on the unit circle a Cantor set of directions, this is also not possible. It will give you an unbounded operator. Okay, what is possible? So suppose I want to find an infinite set of directions so that the operators are bounded. Well, it was known from the 70s, late 70s, early 80s, that if V is a finite order Lacunary set, then I avoid Kakeya context. Now, what is a finite order Lacunary set? You can think of directions that converge geometrically fast to a given direction. Here, I take directions that converge to the basis vector 1, 0 geometrically. This is a first order Lacunary set. There is a higher order generalization, which is not maybe so important for this talk. So there is a class of sets that are infinite. They have very special geometric and combinatorial structure for which the operator is bounded. The maximal operator is bounded, okay? And this, the positive direction goes back to Cordoba and Pfefferman, that they did Wickel 2. Then Egelstein-Wenger proved it for all p greater than 1 using Fourier methods. So here we have geometric methods. Here is Fourier analytic methods. Then Scheger and Celine, they generalized this to higher order Lacunary sets, which I haven't defined, but somehow it's a higher order generalization. And quite recently, 2015, Parsep and Rogers gave a higher dimensional definition of what Lacunary set is, which is not obvious. And they proved that under this assumption, the operator is bounded. So an interesting sort of question has been around for a while and asks, okay, what about the opposite? So assume that this operator is bounded. Is it necessary that V is Lacunary? So there is a famous paper of Bateman, in 2009 in Duke that says that yes, if MV is bounded on LP for some P, then necessarily V is Lacunary, and then it's bounded on all LP space. However, very recently, in May of this year, Hagelstein, Radillo, Murguia, and Stokolos, they showed that the proof of Bateman has a gap. Okay, they didn't show that the result is wrong. They showed that the proof has a gap. So at this point, this result is in question. I mean, this becomes relevant again. We don't know at this point if this is. We don't know the answer to this question.
This result is true for if what are the so on that for NEP if and that will imply he is Lacunary.
So Bateman's so Bateman's result says the following: that if MV is bounded for some P finite, then necessarily the set has to be Lacunary, and then it's bounded for all P by the positive results. Okay.
Okay.
So it's a 0-1 situation. Either bounded for all P or for no P. But the result, as I mentioned, well, maybe it's wrong. We don't know.
Okay.
So now this has become relevant again. Okay, this was for the maximal function, but the Hilbert transform, even if you assume that you have lacunary sets that avoid the Kakeya counterexamples, it's still unbounded. Okay. There is a counterexample of Karagulian in 2007 in 2D that was generalized in higher dimensions by Laba, Marinelli, and Pramanik recently in 2017 that says that for any set, there is a lower bound that is square root of the log of the cardinality of the set. So if a set is infinite, immediately this is unbounded. Okay. This counterexample is not of Kakeya type, is of, let's say, maximal rearrangement type, in the sense that in Hilbert space, let's say, if you have an orthonormal system, you can rearrange it so that the maximal partial sums become bad, they diverge. There's a variety of such results in the literature, and this is the principle behind this result. Okay, so it's not of Kakeya type at all. It's kind of a maximal partial sum type. So okay, if the set of directions is arbitrary, we know that we cannot say something in general in terms of boundedness, but we can quantify somehow how badly these operators fail to be bounded by taking finite sets and trying to prove bounds in terms of the cardinality. Okay, and this goes very much into the direction of the Kakeya conjecture. Just to point out, going back here, that if you fix delta in this, let's say, discretization, well, V delta is finite, has cardinality 1 over delta on the unit circle. And in that sense, for delta fixed, this operator is bounded. And in fact, this is the bound. And as delta goes to 0, this goes to infinity. Okay, so you can think of 1 over delta here as cardinality. So, however, here there is a further relaxation, because we don't assume any structure on the set. We assume just that it has finitely many directions, but we don't assume that it's equispaced or anything. So under this assumption, Katz in 99 proved that the best possible Wigel 2 bound for the maximal function is square root of log, and there is a jump from Wigel 2 to L2, it becomes log. This paper came more than 20 years, 25 years after the results of Cordova and so on for the Kakeya operator in L2, and it's completely different. It's much more hard in 2 dimensions. These results are optimal. Okay. This is a paper of Katz and Cuk. Now notice that if I just take the single scale operator, average at scale 1, but supreme over directions, and I try to bound this in Ln over n, this is not a coincidence, this implies the maximal Kakeya conjecture. Okay, which, okay, I mean, for the ones who know, you know about it, you know, for the ones who don't, it's one of the most important conjectures in harmonic analysis, and it's notoriously hard and open in dimensions 3 and higher. And basically, this bound would imply that Kakeya sets have a lower bound on their Hausdorff dimension. So we know that this is a very hard question. That's the point here. But okay, if we stay, if we stay below the Ln, below the critical integrability component, we can ask what about the L2 bounds? And recently, with Francesco Di Plinio, we proved the optimal bounds for such operators in L2 over n, where, okay, here I just, instead of taking the whole sphere, I take any subset of directions that lie in a subvariety of the sphere. And now M is the dimension of the variety, so you can think of M as the dimension of the parameter space, because V lives in this variety. And now this bound respects the dimension of the variety. Okay, and this bound is optimal up to arbitrarily small losses, which we cannot get rid of right now, and we don't know if they should be there or not. Maybe not. So this means that for every epsilon, there is a bound like this. Previous results, 3-dimensional case, and this being the whole sphere, was due to Cipri and Dimitar 2012. And the case of the curve, so algebraic variety of dimension 1, is a critical case. This becomes nothing, and this becomes just epsilon losses. This is due to Cordova. In particular, it's a logarithmic blow up in n in this case. Okay. What about the Hilbert transform? Now there is a specific proof for the Hilbert transform that uses the structure of the multiplier. Uses the fact that the multiplier can be taken as 0 in a half space and 1 in another half space. And then this provides an easy proof once uses the Rademacher-Menshoff theorem, which is not very difficult to prove in any case. And it shows that L2 bound is of the order log n, okay, above and below. And this is due to Cyprian and Francesco. Now, if you have more general Hermann-Michel multipliers, even in 2 dimensions, it turns out that this problem is much harder. Well, I will explain. So the only proof we know for general multipliers, even in 2 dimensions, is due to Dimitar, and it relies on a very deep result of Lacey and Lee. Sorry. So this proof relies on the result of Lacey and Lee that I will describe below, which in particular contains the Carlson theorem. So realize that the difficulty from Hilbert transform to general multipliers is huge, unless there is a proof we are not aware of at this moment. But the proof we know is quite deep. And this is a combination of these results of Lacey and Lee and kind of a very clever use of the Chang-Wilson-Wolff inequality. Now, if it happens that V is a subset of a lacunary set of directions in any dimension, then recently with Natalia Comazzo and Francesco Di Plinio, we proved that the optimal bounds are square root of log n. So you gain a square root of log if you are in a lacunary set. This is best possible. And again, here it's general multipliers, but the lacunary case is simpler than the case of arbitrary directions. And in higher dimensions, if it's arbitrary, there is a proof of Yong-Chong Kim and Malabika Pramanik in 22, sort of following this result that was for the averages, that proves the sharp bound for arbitrary directions in L2. Again, okay, this proof is much harder than the Rademacher-Menshoff, no comparison. But it uses the special structure of the multiplier of the Hilbert transform. At the moment, we cannot generalize to other multipliers. It used some algebraic facts about the multipliers of the Hilbert transforms that we don't know how to bypass. Okay, so going a bit further into the main topic here, remember the linearized versions of these maximal operators, where I choose a measurable vector field to replace the supreme in the directions. Now, Zygmund first suggested that if this vector field is assumed to have sufficient smoothness, then this should avoid Kakeya counterexamples. And in particular, okay, if you play with it for a moment, you realize that alpha Helders with alpha less than 1 is still not enough. You can still construct Kakeya counterexamples. Zygmund suggested Lipschitz. Okay, suggested that the vector field should be Lipschitz, and we should truncate the scales more or less at the inverse of the Lipschitz constant. And then the operator should be weak type to 2 and bounded above L2. And similarly, Stein conjectured the same thing more or less for the singular integral. So these are sort of two underlying conjecture guiding the research in this area to a large extent. What do we know? If V is analytic, is real analytic, then yes, it's true. It is due to Bourgain for the maximal function and to Stein and Street for the Hilbert transform. Gore gave a different proof of the result of Bourgain, sort of more geometric proof. And Bourgain's argument basically, okay, real analytic hides a bit what is under this, but you can sort of break it up into 2 main ingredients. One is a bit better than C1 for the vector field. And the second is a geometric condition on the vector field that says that no integral curve is flat. So you need some kind of curvature condition on the vector field. And then you can more or less reproduce Bourgain's proof, and that's discussed in several papers, in the paper of Xiaoming, among others. And underlying this also considerations, and also the result I mentioned before, is one of the strongest results we know in this field, which is the result of Lacey and Lee from 2006, that says that if I take band-limited functions that have frequencies in an annulus of frequencies about 1, think between 1/2 and 2, for example, then yes, the operator is weak to 2 and strong LP for P greater than 2. Okay. This is the result of Lacey and Lee. And a moment's thought shows you how this contains, even the band-limited version contains Carles's theorem, because what this operator is doing, remember the Hilbert transform keeps some frequencies in a half space. So if I fix V, I take V perp, I keep the frequencies in this half space. And think of F is band-limited in a, let's say, live somewhere here. But I can more or less approximate a function that just lives on a line. Okay, this is not a function, it will be a measure, but I can approximate the situation. And now what this directional Hilbert transform does is it takes this line and it cuts the frequencies from here and rightward. And that's the Carlson operator. Okay, so this implies Carlson's theorem on Fourier series. And a big open question, I mean, is whether you can do a vector valued estimate in the Lacey proof where you take the small L2 square function in the little Paley annuli of, let's say, radius about 2 to the k. But note that with what we know now, this, if you solve this, you solve the whole conjecture. So this is a deep question. What else we know? There is a proof of Bateman about vector fields that depend on one variable. Okay, and there is a proof of Bateman and Thiele under the same assumption that removes the band-limited assumption under this restricted vector field. You don't go all the way to 1, but you go down to 3/2 from what we know now. The rest are technicalities, and you don't need to worry about them. And also there's a more general sort of proof of the Plinio, Guo, Thiele, and Zorin Kranich, where in fact they prove they show a strategy of proof that in particular works for vector fields depending only on one variable that is more general. Okay, so let me go now to somehow the content of our paper. I just write here again the definition of a directional multiplier in 2 dimensions and note that this is in dimension 1 and the functions are in dimension 2. The codimension is n-1. Okay, in this case is 1, but in general, you can think of codimension n-1. And so now we go to Rn and we take a Hermann-Michel multiplier in Rd. Okay. And we form the corresponding object. Okay, so this depends on d variables. I take a basis of an element of the Grassmannian of d-dimensional hyperplanes in Rn. And I plug in xi dot the first vector and so on. And I calculate this object. This depends on the variable, so this is fine. And now I take the supremum over orthonormal basis that span sigma. And the supremum over sigma. Sigma is a d-dimensional hyperplane in Rn. Of course, D can change orientation, right? It's not fixed. That's the point. That's the directional aspect. And okay, there's a new element here that I allow M to depend on sigma, and I want all this M sigma to have uniform Hermann-Michel norm. An example, okay, here I just add sigma in the sense that if I take the supreme over a subset of the Grassmannian, I hope to keep that information. Okay, so an example, just think of the vector of Riesz transforms in Rd. These are the multipliers, which after a bit of work, you can see that this is the way you define this directional singular integral. Okay, this corresponds to the vector of the Riesz transforms. And P sigma is the orthogonal projection on C. Okay. How do you calculate this operator? You take an xc in Rn, you project it on sigma. Okay, you normalize us in the fashion of the Riesz multipliers, and then you form this Fourier integral operator, and now you take supreme over all elements of the Grassmannian. This is our object here, and the main theorem is the analog of Lacey-Lee, but in any dimension and codimensional. So weak type 2 for band-limited functions and strong LP type for P greater than 2. And what about this dependence on sigma? We need, okay, if M here, if this multiplier M here does not depend on sigma, for example, as in the case of the Riesz transforms, then of course the map that takes, sorry, the map that takes sigma to M of sigma is independent of sigma, so this is always continuous. But if it's not, we need a very weak Lockhelder continuity assumption that I will come back to. Hopefully, I will have time to explain where this is needed. Note this, I mean, I don't know if there's some confusion here. This multiplier does not depend on sigma. Okay, of course, I mean, once you plug in the projection, it does, but that's not what I mean. This multiplier is the one that generates the singular integral, and this is independent of sigma. Okay, this projection will appear because of the way this is defined, so this is not a problem. For this, you don't need any assumptions. Okay. And as a corollary, we can get the sharp, let's say, quantification of the blow-up of the norms, of the two norms of directional codimension 1 multipliers when the subset of the Grassmannian has cardinality at most n, and this is log n again, as before, as in 2D. Okay. And of course, here there is no easy proof of that, and you need to use the whole machinery that gives this theorem. And just to give an indication of somehow what is contained in this theorem, I mean, you can use this theorem to get the Carlson-Selin theorem for maximally modulated Hermann de Michling multipliers, which is essentially a higher dimensional version of Carlson's theorem. Of course, we know this theorem is true anyway. In fact, we even know it in the non-translation variant case. But somehow this theorem here contains the Carlson-Selin theorem, just to give an indication. Okay, let me start commenting on some aspects of the proof. I think I have maybe 15 minutes or something like that.
Yeah, you have maybe, usually you can talk up to 4, I think.
Until?
Until 4. Oh, okay. I think
you have half an hour.
Okay.
Half an hour.
Okay, that's more than enough. That's plenty. Okay, so let me point out a certain new aspect in higher dimensions that was not present before. So if you look at this definition, this is an orthonormal basis of some element of the Grassmannian sigma, and this I will take supreme over sigma. So imagine I take a rotation that maps this basis to another basis. Since I take supreme over sigma, nothing will change here. Okay, so there is a rotation invariance embedded in this definition. And I can rotate the basis of the elements, the basis. I mean, take any rotation that keeps sigma invariant, basically, and nothing changes. And now this is a bit of a problem for us because the methods we have are not rotation invariant. And for a moment there, we were a bit troubled if this is too large of a parameter space to give a bounded operator. But it turns out there is a way to remove this invariance, and I will explain this now. So here I just explained that there is this invariance because one can rotate the orthonormal basis to another one and nothing really happens. Okay, and this can introduce artificial discontinuities in the following sense. So imagine you have the standard basis of RD, and now you want to map this into a basis of sigma, and imagine that sigma is very close to RD. It's a small perturbation. Now, there is a way to do that in a continuous way, where when you look at where a basis vector is mapped by the rotation, this is very close, so there is some kind of smoothness, or you can map it to the close one and then rotate sigma and make it completely arbitrary. So this becomes very discontinuous if you do that. However, you don't need to worry about this, and in the sense that you can choose your favorite way to map sigma to RD, and that is because of the following sort of theorem on maximal multipliers, and it's much more transparent to explain it in the non-directional world. So just look in RD, think just RD, there is no directions here, and take a nice multiplier, and now rotate this multiplier and take supreme over rotation. Okay, this is defined as a linear operator, and the question is this bounded? Without the sup, of course, this is bounded. This is a Calderon-Zygmund operator. But what about the maximally rotated multiplier? And a priori, there are problems here. For example, if instead of rotations, one considers dilations, one considers the maximally dilated multiplier, then this is unbounded. Okay. This is due to a counterexample of Chris Grafakos, Hosnik, and Seeger. In general, even if you take dyadic dilations, this maximally dilated multiplier would be unbounded. What about the rotated version? Well, what saves the day here is that the group is compact. And the proof goes a bit like this. It's not very difficult, so I can sort of show it in one slide. So let's just write it in 2D because I can parameterize very easily the rotations and fit it in one slide. So this is the rotation. I define this multiplier, and this depends on the rotation theta. And now using the fundamental theorem of calculus, I can write the operator at theta as the operator at 0. Well, 0 is not important, at any fixed rotation, plus the integral of the derivative. Okay, and then putting the absolute values inside, I have this guy. This is obviously very tame. It doesn't depend on theta. And now I have an average of some singular integrals rotated at different places. One can very easily calculate what are the symbols of these operators because it's just, you know, taking derivatives of these multipliers. So this is exactly the symbol here. And it's an easy calculation to see that the Hermann-Michels estimates for these multipliers are following by the ones for M uniformly over rotations, with the only caveat that you need one derivative, because here you kill one derivative of M. But okay, in these considerations here, we don't care about how many derivatives we assume for M. So we don't care if we lose a finite number of derivatives. So we just start with M that has more derivatives, and then this is fine. Okay. So if you do that and you use Minkowski inequality, you see immediately that this is bounded. The maximal operator is bounded, right? Because this does not depend on theta. And here I can take supreme. And that's the idea that removes the invariance, okay? Okay, so with that being said, now I can write a more specific model for my operator. And it's kind of a lot here. Let's try to unpack it a bit. So I have a family of multipliers M sigma. They depend on sigma. Sigma is an element of the Grassmannian or p-dimensional hyperplanes in Rn. Now, P sigma is the orthogonal projection. So I take a xi in Rn, I project it to sigma. And remember, M sigma is defined on Rd, so I need a rotation that will map sigma to Rd. Okay, so P sigma maps to sigma, I rotate it to Rd, this is now well defined, and I take supreme in C. And by the discussion before, exactly because I can choose what rotation I can put here, I can take a nice one. Okay, I can take a C1 in the topology of the Grassmannian. Of course, one needs to prove that such rotations exist, but this is not difficult. Okay, this is done. If you take the intuitive one, you will see that this is the nice one. So we can choose here, although this was not a priori apparent in the definition, a nice rotation that maps sigma to Rd, a C1 rotation. Okay. And also, the problem is rotational invariant in general, in the sense that I can take a subset of the Grassmannian that is very close to Rd. Okay, how do I do that when I want to calculate the supreme over all the Grassmannian? Well, I take a 1 over 1 million net on the Grassmannian. Okay, so in each subset, my elements are close to some fixed d-dimensional hyperplane, and I rotate everything so that it becomes Rd, and I look at only one of them. Okay, so that's nothing. And now, if you look at the, well, this multiplier is a multiplier on Rd, that's Hermann-Michels, so the only frequent singularity is at 0. The way I define this acts trivially on the perpendicular variables, which means that the 0 singularity propagates in the whole perpendicular line, and this I span by V sigma. V sigma is the perpendicular vector to sigma. So these multipliers have frequency singularities along sigma perp, which is spanned by the vector V sigma. So if I take a small cone around En and use the assumption that my sigma is close to Rv, meaning that V sigma is close to En, I can contain all the singularities of the multiplier in this cone, and outside the cone, nothing interesting is happening. I can control everything by a usual Hardy-Equilibrium maximal function. Okay, so what is left is the piece of the function of the frequencies inside this cone. And I have also a band-limited assumption. So my function has frequencies that are of modulus around 1 and contained in a small cone around E. And I will continue with this assumption from now on. And for such function, I want to discretize this operator. Okay, that's what will be, that will be the main topic of the following slides. And we will use time frequency analysis to do that. So before going into this operator that is somewhat a bit more complicated, think of a Hermadel-Michny multiplier on the real lines. Okay, just on the real line. It's singular at 0. So how do we discretize in frequency? Typically, we take a little pale decomposition. Okay, so we break it up into smooth pieces that are of size about 2 to the k, and the distance to the origin is about 2 to the k. So that's already discretized in frequency. And now when a function is supported on a frequency interval of length 2 to the k, it's roughly constant at physical space scales of the inverse, like 2 to the minus k. So you can discretize as a sum of pieces in space of length about 2 to the minus k. Now, this piece will not be compactly supported because they are because of the uncertainty principle, but they will be very, very concentrated on some interval. So we will try to imitate this in the directional case. So fix a sigma. Remember, now the role of 0 is played by sigma perp. And do a little pale decomposition in the sigma variables. So I take annuli of distance from sigma perp about this. Okay, and this S will be like 2 to the k. So I break this up as a sum of frequency pieces, each one supported here. The projection of xi on sigma is about S to the minus 1. S is a scale. This means that the distance of xi to sigma perp, okay, this p sigma is essentially this distance. Okay, I will come back to this notation later. And now, once we fix a sigma here in this frequency discretization, I want to discretize in space. So first, I do the following. I take a single scale Gabor decomposition of the function. And how I do that, I take a delta net on the unit sphere of radius s minus 1. So a finitely overlapping cover of the unit sphere of scale s minus 1, and these betas are the center. And these are smooth bumps supported in these caps. Okay, I need to take two of them for technical reasons. Don't worry too much about that. Okay, these are I already said. And yeah, so this decomposition of the Gabor decomposition is single scale. The scale is fixed here, s minus 1. So I write f as a sum of pieces. So this is the picture. When I fix s, f is supported here in frequency. And now I break up this annulus into tubes given by these caps. If I give you the cap, I can form the tube, and the size of these caps is s to the minus 1, and the center of each cap is beta. Beta is the s minus 1 net. Okay. Okay, so this way we discretize everything into pieces. And how do these pieces look? Well, in frequency, this is a cap of center beta and scale s to the minus 1. This one is because, remember, my function has frequency support around the single annulus, x equals modulus of x equals 1. Okay, I will call this omega t. And now this is the dual object in the sense of the Fourier side. So if I go in space, a function that is supported in such a piece can be discretized as a sum of pieces. In particular, this will be parallelepipeds, such that the perpendicular vector is beta. The scale, the main scale that we are interested here is the one perpendicular to beta, and that's the inverse of this one, so S. And this is 1 because this is 1. So this is just the inverse of 1, which is again 1. If this was an annulus of length A, this would be 1 over A here. Okay, and this I will call R. This will be the special support. So functions here are essentially constant on such things. So I can write them as a sum of such things. In order to organize this in a time frequency function, I call this tile. So Cartesian products of a space component, which is a parallelepiped, and a tube in frequency. And the uncertainty principle, I have already enforced it here, says that the product of these guys is 1, as it should. And putting things together, for each sigma, I mean, putting the decomposition of the operator and the function, I will get a wave packet coefficient. This is the wave packet phi. You should think of phi as supported in frequency in omega t in this tube, and in space in this RT. Of course, in space, it cannot be compactly supported because I asked that it's compactly supported here, but it has Schwarz tails. It decays very fast away from this, okay? And now what is this? I come back to the previous notation. Remember, this was the single piece of the little Paley decomposition. I call this psi s. You can think of this as a single scale piece of the operator. This is a breakup of the multiplier. In particular, because since you're away from the singularity, this has a kernel. And it lives at single scale, as frequency scale s-1, space scale s. So this part here is a single scale piece of the operator acting on the wave packet. Okay, and I give it a name. I call it theta t. Now this depends on sigma because remember that the little Paley decomposition we did was in the sigma variable. So if you change sigma, this changes, and also it depends on sigma because the multiplier depends on sigma. So this somehow is, for fixed sigma, you can think of it as a wave packet because the single scale action of the operator doesn't do much. But the problem comes from the fact that it depends on sigma. And remember, I need to take supremum in sigma. And okay, of course, it's not completely clear. This was just a sketch, but you discretize this operator in a collection of such tiles, and then by easy approximation arguments, you can take a finite collection of tiles. This is just for not having to worry about convergence issue in the sum. So, and now this is my model for fixed sigma. What do I do with the supremum? Sorry, before that, let me just repeat because this is quite complicated. So this is my frequency component. You can think of the frequency component as the cap on the sphere, qt, or the tube, omega t. The tube is just the cap times length 1 in the direction. This was beta. I will need to define the central part of this cap and the central part of this tube. And this is only for people somehow that are a bit familiar with time frequency proofs. Usually we want to put the support of the wave packet deeper inside the frequency component, okay? This is useful for a point that I will explain later. But you can think of this cap or the center as the central support of the frequency support of the operator. Now, the main thing that allows us to deal with the supremum is the choice function. So with this setup and considerations, one can show that if we go to the model sum, this is a sum over tiles, a tile will survive in the sum, will give a non-zero contribution, if and only if the perpendicular vector to sigma belongs to a certain subcube. Okay, we can fix the position of this subcube by, I mean, a priori it will belong to any cube that is not the center, and then by splitting we can say it's this one, the one in the bottom left corner, for example. Okay, so the tiles that survive in the sum are the ones for which V sigma belongs to a certain subcube of the frequency component of the tile. And I incorporate that in the model operator as follows. So I take my original operator, I pair it with a function g in order to do a duality estimate. I write the model sum, where now, since I have a supreme in sigma, I linearize by taking a measurable choice of elements of the Grassmann. Okay, this is the same as I did before with v of x. Now it's sigma of x. And here, okay, I need to do a technical modification to take care of the absolute value, but this is completely unimportant. And now I can insert for free here an indicator function that will tell me that a tile will survive in the sum if and only if V sigma is in a certain subcube. That's what I explained previously. So doing all these things gives us the model operator, which is discretized in a time frequency function. And there is an arbitrary choice of measurable elements, I mean, a measurable choice of elements of the Grassmannian. And I know essentially nothing more about this except that it's all the sigmas are, say, close to RD by an absolute constant. Okay. Now, the rest is somehow quite addressed to people that know at least the proof of the Carlson theorem. So if you look at this operator, you will realize after a moment that it looks very, very much like the discretization of the Carlson operator. The Carlson operator is a maximal sum of truncated Fourier series. The level of truncations corresponds to this measurable choice. Okay. In Carlson, we need to choose a measurable truncation. Here, we choose a measurable choice of elements of the Grassmannian. And where the log Dini assumption comes into play, let's talk a bit about trees. So I have a bunch of tiles, and I will call a subcollection of tiles a tree if all the frequency components contain a certain unit vector. Okay, this is here. And all the space components intersect a parallelepiped, okay, the fixed parallelepiped of larger scale. Okay, this definition probably doesn't tell you very much. You should think that a tree in the labyrinth of tiles is a Calderon-Zygmund operator. So in trees, we find Calderon-Zygmund structure. Okay, the original operator has modulation invariance. There is no particular frequency that plays a fixed role. In the trees, we fixed a top, we call this the top, and this frequency plays the role of 0 for Hermann-Michel multipliers. So in trees, we see Calderon-Zygmund theory. And of course, there are many trees in the collection of tiles, so we need to somehow deal with them. And we sort of distinguish two types of trees, the ones where these top frequencies in the place where the vector field should be, and the one where it's not. And this we call the lacunary case, and this we call the overlapping case. Here, the term overlapping comes from the fact that all the supports of the frequency supports of the wave packets overlap. And the lacunary here comes from the fact that all the frequency components of these tiles have a Whitney type structure. Okay, I won't go into the details of the proof. First, you prove an estimate for a single tree, then you need some sort of greedy algorithms to deal with the different trees. But for a single tree, which you remember that I said that we can think of it as a Calderon-Zygmund operator, we want to get rid of the dependence of the directions. We want to assume that everything has a fixed direction. And mostly this is possible. Okay, for example, by rotation, I can assume that this top frequency is the vector En, and then everything is axis parallel once I do this assumption. So the only thing that remains as a dependence on sigma here is, let me go back to the model. This depends on sigma. Okay, so in a tree, I need to pass from theta, whatever depends on sigma, to theta, and put here the top of the tree, let's say a fixed element of the Grassmannian. And in order to do that, I need some kind of continuity estimate. Okay, the first one is the trivial one; it always holds. This is the assumption, essentially. And in order to prove the second part of the estimate, I need to assume something for the multiplier, and I assume exactly this type of log Dini modulus of continuity. So if I take m sigma and m rho, where sigma and rho are two elements of the Grassmannian, and I look at the difference of m sigma and m rho in the Helmanden-Michel norm, it should satisfy such a continuity estimate. And with that, I can prove the whole thing. Okay, of course, most of the details here are skipped. Okay, but in any case, this is where it comes. It comes in the single tree estimate and nowhere else in the proof. Okay, and if you have a single multiplier, then it's fine. You don't need this. It's automatically satisfied. And let me just comment very briefly on the corollary. So how do you get the estimate for finitely many directions? I will not go into detail, but I will put on the slide two ingredients. The first is a consequence of the Chang-Wilson-Wolff inequality. The Chang-Wilson-Wolff inequality says something of the following type, that if you have a martingale square function in L infinity, their function is exponential L2. Okay, it's very unclear how this comes here. I understand that, but it can be used to show that if you have a supremum over n multipliers and the multipliers have uniform L2 bounds, then I can insert L2 L decomposition, this PKs are L2 L decomposition, by praying a square root of log n. Okay, this is essentially in the paper of Rafakos, Honzik, and Seeger, but in this, I mean, you cannot really use it as a black box. You have to open the proof, and this was done by Dimitar in the paper in Proceedings of AMS in 2010. So you can think of f as a sum of the little Lupelli pieces. Usually we have little Lupelli theory, we can take the square function and these norms are equivalent, but here we cannot because we have the supremum. So this tells you can commute the little Lupelli square function by paying a price of square root of log n. That's one ingredient that was more or less available before. And okay, I repeat this here. And the other ingredient is the following. We prove a weak L2 inequality. Remember, the theorem doesn't have a strong L2 inequality. We prove a weak L2 inequality with absolutely no loss. Now, if you have a finite subset, you can upgrade this to an L2 estimate, but you pay a price, square root of log. And this is not difficult. I mean, you have an L2 estimate with a uniform bound. And now when you have a finite number of multipliers, you have a trivial weak L1 estimate, let's say, with a polynomial growth in the number of multipliers. And similarly, you have a trivial LP estimate with polynomial growth for p greater than 2. And now you do interpolation. And you can, if you do it in a careful way, you will get this. So you upgrade the weak L2 to L2 by paying a square root of log price. And now you put these things together. Essentially, you do little Lupelli theory with a square root of log loss. And now you have the square function in L2, so you can commute the sum. And once you take the sum outside, this is essentially the corollary of our theorem. This is again another square root of log. You put them together and you get the result. And the result is sharp. I mean, you can show that by taking non-counter examples, essentially. A radial function will do here. It's not difficult to prove that this is best possible. And note that I used also that have the square function in L2, right? So if I have the square function in LP, I cannot do this trivial calculation. And these results, even 2-dimensional for p greater than 2, are not known. We don't know for general multipliers what is the sharp, or even for the Hilbert transform, we don't know what is the sharp LP bound for finite subsets. And with that, I would like to end here. Thank you very much for your attention.
Thank you, Ioannis. And is there any question from the audience?
Okay, so I have a question.
Yes.
Could you please go back to the directional maximal function MV?
Yeah. Here.
Yes, so here instead of taking supremum over all positive real number,
Yeah.
if we just take supremum over a fractal set,
Yeah.
with Hausdorff dimension or Minkowski dimension less than 1.
You mean in the scales or in the directions?
In the scales.
Scales. Okay. Yeah.
So does there any result of boundedness?
Okay, so let me just point out something, that the counterexample, let's say the Kakeya type counterexamples, but also other types of counterexamples, exist already at the level of the single scale. So even if I fix R to be 1, the Kakeya counterexamples are relevant because Kakeya is a single scale counterexample. But yes, your question makes sense. I mean, so you first have to formulate the question on this level of the single scale operator because this is already problematic, right? So, but you can ask the question you asked for V having a certain dimension. Okay. So imagine that your set V has a certain, I don't know, Minkowski dimension, for example. And indeed, there are results of this type. At least for radial functions, we know that this operator is bounded for p greater than 1 plus the dimension of the parameter set. If the parameter set is the whole sphere, is 1 plus 1 is 2, is the critical exponent in R2. But if, like you said, you have a fractal dimension, it will be 1 plus this dimension. But however, in general, these operators will always be unbounded, even for sets of fractal dimension less than 1. It's just that where is the critical LP space where you change from polynomial growth in the cardinality to epsilon losses to logarithmic. But yeah, the question is relevant, but you have to set it up a bit carefully.
Okay. Thank you.
You're welcome.
So any more questions from the audience? Any more questions? Okay. If there are no more questions, let us thank the speaker for a wonderful talk.
Thank you very much. Thank you for attending.